Welcome to the next video in linear models. This is video 2 on random vectors and matrices. It corresponds to chapter 1 of the textbook. So let's start by considering a situation where you have a matrix of variables, and this is just like having a matrix of a bunch of numbers, except that we can assign values to the variables just like you would with any function. So x is, effectively as a matrix of variables, it's a function, right? And then suppose that we have an appropriately shaped vector of constants, which we're going to call the vector beta. And then we can matrix multiply the matrix of variables times the constants. So here's a little sort of specific case of a 3x2 matrix and a 2x1 vector. So this is all variables, this is all constants. And when we matrix product them, we get this vector, this 3x1 vector, and it is filled with a bunch of variables. So the idea here is that if you assign values to the variables, then it takes you from all of those variables to a vector. So that effectively this is a way of defining a multivariable function. That's really what this is. It's a multivariable function that gives you as an output a vector. Now this is a lot like a generalized linear function that passes through the origin always, right? It's sort of linear because each of the components is like this linear combination of some of the variables. So it's like a linear function, but it always passes through the origin because you could always set all the values of the variables to 0, and that will necessarily make this vector the 0 vector so that it's always possible to pass through the origin with this kind of a function. Now, to sort of generalize from here, we could have another constant vector a, and we would get what is much more like a general linear function by putting x beta plus a. So this will not necessarily always pass through the origin, especially in the one-dimensional case where x is 1 by 1 and y is 1 by 1 and so on. Then this is a lot like the familiar linear function that may or may not pass through the origin. Now, what we're actually going to be interested in is what happens if we take that a and rather than have it as a constant, we instead take a vector of random variables. Such a thing, right? When you form such a function, so the inputs are some real numbers that are inputs to the variables in the matrix X, and the output is a vector, this time of random variables. We call this kind of thing a linear statistical model, and that is the backbone of everything that we're going to study in this course. Here's a bit of a graphical attempt at depicting what's going on. So if you think about the matrix X times the vector B, then, now I'm drawing something that's in the sort of like 1 by 1 case, right? So X is a 1 by 1 matrix, Y is a 1 by 1 matrix. And so this is a limited case, it's a limited drawing, and it's going to strain my artistic ability to try to represent what I'm trying to talk about here, but hopefully this makes some amount of sense and gives you a little bit of an extra grasp on the topic. So again, xb is like this linear function that passes necessarily through the origin. We're interested in talking about xb or x beta plus e. And so if you specify the coordinates of x, right, then you can compute x beta, and that gets you to some particular point on this line through the origin. Once there, you sum e, and that's a vector of random variables. Again, here we're talking about the 1 by 1 case, so e would have to be a 1 by 1 matrix, which is to say it is just a single random variable. Anyway, so then what we're talking about is that basically x beta makes up the center, or at least it shifts the center of the distribution of this random variable, but e, is whatever it is, right? So this is me trying to draw the probability distribution of this random variable e. And I'm kind of depicting it as having its center, its expected value centered right on this point. And if it's not clear, the intention here behind like how I'm drawing this, and keep in mind it is just a drawing, so don't take it too literally or meaningfully, but it's just to try to help to communicate the picture of what's going on here. And so what I'm trying to do is I'm trying to represent this probability distribution as like coming up out of the page, right? So x and y, those are axes that are inside the page, and you can kind of move around, right? Like this matrix x beta, kind of depending on the values of x, can send you to some point in the xy plane, but that's inside the page. And once you get to that point, then there's a probability distribution there coming out of the page. And you can do that at every single point. So if we came down here to this point, there would be another probability, right? It would be basically the same probability distribution, just shifted down to this other point on the line represented by x beta. So essentially what I'm trying to communicate is for each choice of the values of the variables in the matrix X, you get a random variable at that point, basically. That's what I'm trying to represent here. Now, that is kind of the general case where we really don't know anything about the random variables that are inside of the vector E, but there are some very common assumptions, if not the whole time, then nearly the whole time we are in this course. We will assume the following properties of the random variables in the vector E. We will assume that every one of those random variables has mean equal to 0. We will assume that they all share the same variance. And here I think I have a typo. I believe that should be the variance of EI equals the variance of EJ, no matter what the choice of I and J are. So they just all share the same variance. And another way, right? So here I'm kind of telling you these constraints, these assumptions that we're going to always make about this vector E. I'm telling it to you here, coordinate by coordinate, but there's an equivalent way to tell it to you in the language of vectors and matrices. So in the language of vectors, I would just tell you that the expected value of the vector E is equal to 0, the 0 vector. That means the same thing as saying every single individual random variable has expectation equal to 0. So these two things say the same thing. This one just says it component by component, and this one says it in the language of vectors. And then likewise over here, these two things, this thing about the covariance of the vector E says the same thing as what I was saying earlier, component by component, right? So this says component by component, that any two of these random variables share the same variance. And here we're saying that if you compute the covariance of the vector, and you can go back and remember what that means, like that's the matrix of all of the covariances of the two random variables. And so we're saying that it is the matrix with a single value, right? This sigma squared, that's their shared variance, right? Sigma squared is the shared variance of all of these random variables. And it's, like times this identity matrix. So this basically means that we've got the matrix here. Let me somewhat draw that matrix. It's going to have sigma squared, and so on, all the way down the diagonal, because we're doing sigma squared times the identity matrix. And down here, it's going to be all zeros. Up here, it's going to be all zeros. And effectively what we're saying when we say that their covariances are all 0 between any two distinct, right? Because a 0 down here would mean that you're talking about some EI and some distinct EJ, and we're saying that those two separate random variables, we're looking at their covariance, we're saying that that covariance is 0, meaning that they're independent. So anyway, so independence is yet another assumption that we're going to make about all of these random variables in the vector E. So that's why we get all these zeros in the covariance matrix. So these are the standard assumptions that we're going to make about the vector E, right? This vector of random variables. Now, throughout most of this course, we're going to be interested in developing point and interval estimates for the random variables involved. We are going to want to design tests for beta and for sigma squared, right? Because those are often going to be values that we hypothesize, and then we would like to test whether the some given data confirms or disconfirms our hypothesis. So we'll want tests for beta and for sigma squared. And we'll also want procedures for model selection, and that has to do with like forming the variables in the first place, right? And we're going to conclude this video with an exercise, and the first exercise, this is given in the book, by the way, so the exercise is to write the following system of equations, and this is really a system of equations because for each I from 1 to 6, we get an equation. So this is a system of equations. But we want to write it not coordinate-wise, but instead write it with matrix notation. Now, one part of this is relatively simple and straightforward. It's the constant term beta 0, right? So that is just constant and shared throughout all of the equations. And so it makes sense that we might give it a constant 1 in, this, by the way, is sometimes called the design matrix. So we're going to give it a column of all ones in the design matrix. And over here, we're going to write our vector of coefficients with the first component being beta 0. What that, in effect, is going to do is mean that beta 0 always gets multiplied by 1. And so that's how this beta 0 term shows up, right? Like you're also going to get this beta 1 times x11, but I haven't talked about that yet. So for now, I just want to focus on the fact that by putting the column of 1s here and the beta 0 here, then this guarantees that, that I'm going to get this beta 0 term in every single one of the equations that correspond to this matrix product. Okay, but now let's talk about this beta 1. Now, beta 1 is also constant, and but on the other hand, there's this variable xi1, right? So for each different I, there's a different xi1. And so I would like to have a beta 1, 1, but I would also like to have a beta 2, 1, which would come here. And I would still like that to be multiplied by beta 1. And keep going, and eventually you get down to when I is equal to 6, and that's going to get you this x61. And when you have x61, yet again, you want to have that multiplied by beta 1. And so, because of the placements in the design matrix and in the coefficient matrix or the coefficient vector, that's going to happen, right? You're going to get that beta 1 times x61, and that's going to happen in the sixth equation. And so, so hopefully this is clear that this is, I put this column of x's so that I get various x's for each of these different equations, but the beta 1 is constant, so I put the beta 1 over here. And that this row of the constant vector is going to kind of line up and get multiplied with this column of the design matrix. At this point, I think it takes very little explanation, right? The same kind of story holds for the third column and the third row, right? The third column of the design matrix and the third row of the constant vector or the coefficient vector. And then likewise for the next one, right? So we just get another vector column of all of those, and they're multiplied by this next coefficient beta 3. But then there's the random variable term. And as I've mentioned before, we like to have the random variable term kind of written off to the side, right? We typically write this as x beta plus the random part. So that's why I've got the random part, which is E1 through E6, whatever those random variables are. We don't know, but we don't need to for this exercise. We have the random part written off to the side, and there you have it. That is our vector, and I should probably put an arrow over that y because it's a vector, and that's the vector of all the yi's, with I going from 1 to 6. Okay, we do another exercise, very similar, but significantly trickier this time, for one reason, and there are a few reasons why this is going to be trickier, but this time we have 3 indices, I, j, k. I is going to range from 1 to 3. J and k are each going to range from 1 to 2. And for each specified I, j, k, we want to have this equation, right? The mu plus alpha I plus beta j plus gamma ij, which is kind of tricky, right? That's like an interaction term, so to speak, but we'll talk more about that later. And then eijk. And you can see down here the design matrix that I came up with, and it's so large and so long that it goes well off of the page, but I'll scroll down in a minute. To begin with, I just want to discuss how I started writing this thing down so that you see the logic of it. Now, the first column is no surprise. It's all ones, and that's because this mu is constant, shared between all of the equations. I think I may have, in fact, I did forget to write down the coefficient matrix or the coefficient vector part of this, but it'll just be mu and then 1, 1, 1. Oh, and I am noticing that I did not do what I am supposed to do, which is to split off the random part. So in fact, we need to delete this last column. So the coefficient part should be mu and then 3 ones. And then off to the side, we would add the vector of random variables, right? Because we always want to write the random part kind of as its own separate term. So this would be E111, E112, and so on. I'm going to just indicate that it goes and so on down to E322. Anyway, okay, but let me explain how I developed this. So again, right, the mu part is really straightforward. It is constant, so we give a column of all ones, and over here in the coefficient vector, we put mu. Now here, because alpha has an index and it changes, then I want to sort of list out all of my possible alphas. And in particular, right, I'm going to have 4 rows of alpha 1, 4 rows of alpha 2, and then down here 4 rows of alpha 3. Why 4 of them? Well, for a fixed choice of I, there are going to be 4 choices for j and k. Right, so j could take the value 1 or 2, k could take the value 1 or 2. In total, the number of possibilities for j and k is 4. So that's why I have 4 rows for alpha 1 and alpha 2 and alpha 3. So this is, in some sense, like the I region of my design matrix. Now, let's talk about the J region, or at least I equal to 1 region. Now let's talk about the J equal to 1 region for my design matrix. And when J is equal to 1, that's going to get me a B sub 1. And so I would like to have B1 in my design matrix followed by B2. But I'm going to have 2 of them. Why 2 of them? Because once I've chosen my I and I've chosen my J, then there are 2 choices left to make for K. So that's why I want 2 rows for B1 and 2 rows for B2. And now proceeding somewhat likewise. And actually, And with I and j having been fixed and chosen, the indices on gamma are determined by that. So that's why I want to have a gamma 1, 1 is because gamma is supposed to have coefficients I and j. But I'm going to want two of them yet again because I still have two components left that correspond to the choice of k, so I need to have two of them here, right? So that's why then down below I have gamma 1, 2, right? I is 1, j is 2 now, but I have two of them because I know that I'm going to want to have a space for when k is equal to 1 and when k is equal to 2 in each case, right? So when k is equal to 1, when k is equal to 2. And so I continue down the matrix proceeding likewise, right? So this is the region where I is equal to 2. This is the region where I is equal to 2 and j is equal to 1. And then this would be the region where I is equal to 2, j is equal to 1, and k is equal to 1. This would be k equals 2. Here j would increment to 2 and k is back to 1, and so on and so on. So I hope that makes sense. And so anyway, I know I've marked up my solution, but basically the solution is this whole big matrix expression, right? So my vector of y variables is equal to this design matrix times this coefficient vector plus this random vector.